We are about to abandon 2 dimensions and move into more exciting stuff. There are many more details, but let's leave it for now and move on to any number of dimensions. Change your pace. We have exhausted everything we can do in 2 dimensions, but there's some lessons which will carry to arbitrary dimension. So the main lessons that Strogatz and I try to emphasize in what we have done so far is that there's a notion of Poincaré section. So I'll do it again. You know, we did it in 2-dimension, and it was a little bit boring because in 2-dimension, I had a motion on the plane, for example, on a cylinder or on a torus, and I could take a line, 1-dimensional object, and as long as trajectory was forced to cross it, I could just count these crossings. But the general picture is very simple. So we always draw it in 3 dimensions, but we really think of arbitrarily many. Thanks to Descartes, we are not afraid. So we are in D dimensions. You know, I don't want to put some ball in it, but we are in this case in 3 dimensions that you're visualizing. It could be 4, 5, 6, 7, infinity, a very large number of dimensions. And in that space, you construct a codimension 1 hypersurface. So for example, this would be a hyperplane. In 4 dimensions, this would be a 3-dimensional hyperplane. 2 dimensions is a line, 3 dimensions it's a plane. And you usually think that you're allowed to bend this thing, and so you think of it as a surface. To make life simple, you know, at least make it a continuous surface, though other things have been done, can be done sometimes. And now this hypersurface is chosen so cleverly that equations that you're solving have a property that if you start any place in this surface, equation moves you out of it. Now, you know, in 1 and 2 dimension, it's easy to understand what it is, but it's also, if this is 99 dimensions and you're in 100, what it means is that you start with a vector that has 1, 0 component to define this hypersurface. The moment you put it in your meat grinder and start making your sausages, it immediately fills up also that dimension. So it's a full dimension trajectory. And if it's not a very boring system that if I start someplace, I just march over it off to infinity and I'm never seen again. If you're confined to the bottom of some valley or anything, you will be recurrent in the sense that eventually you will pierce the same hypersurface. So you started at x0. After some time, which you might need to compute, you will reappear here. And you can think of that as Poincaré map. So this is a Poincaré section, S for section. It just cuts your space. And it's a border between stuff that's on one side and other side. And as long as it's codimension 1, it does splits the space in 2. You can use your integrator to compute a function. The vector in this hyperplane has d minus 1 dimensions because you're 1-dimensionless. And you can write a set of functions, n minus 1 of them. So this is a vector full of functions that says that I started here. Next time I intersect the space, I'll end up at a different point, and going from here to there is not a differential flow. You don't have to know all these details how you got there. You only need to know where you landed. That's called the map. And what that map does is it takes the section and maps it into itself. This picture, there was a 2D section, could be any dimension. No extra thinking needed. And there are magical initial points in the space, in this subspace, where you get started someplace. You leave the hypersurface. You go and you do your complicated dance someplace far away. And then you finally come back. And once you are back, you come exactly to the initial point. Now that I will call a fixed point as opposed to equilibrium of differential equation. You know, in differential equations, we have this property that the special points in a state space where all components of velocity vanish together. But this is totally different. Velocity is big, you know, nothing needs to vanish. But I go around and the map has a property that it takes a point and maps it back into itself. So, you know, this is a fixed point. In this, I differ from Strogat's book. So this is fixed point, and you know, fixed point just means it's a special point that if I start on it, I return to it after one or maybe more Poincaré map iterations. And there is an important detail here. Starting any place in the space, you know, it might take you a minute to come back, or it might take you 7 minutes because you go someplace, do something complicated, return. So there is an important notion that comes here, which is called flight time. And in general, this flight time is a function of the point you started in. So if I start someplace in space-time at point xn, depending where I start, I'll have different flight time. And now what has happened is that I used to have differential equations. Now they're reduced to maps, to functions in discrete time. You know, every time I cross by, I can imagine that's a unit of discrete time. And what used to be a flight time between coming and returning, or in this case, periodic orbit time, is now a property you compute from your Poincaré section. So this is a powerful insight due to only Poincaré. It connects two kinds of ways of thinking about dynamical systems. Time can be continuous and discrete. For people who are raised in engineering and physics, continuous time seems intuitively the right thing. And the way you deal with it is that you do integrations. So you find solutions by starting, let's say, initial point and integrating. Now, if this was course taught in math department and not in physics or engineering departments, then it would be very natural to start with discrete time. And the way dynamics is described in discrete time is by iteration. What does it mean? You start at x0 here. You find the next point using this map. Then you feed x1 into iteration, and you find out where are you 2 Poincaré sections later. So you compose functions by, writing a little program on your pocket calculator, which you compute something, maybe very complicated, you get a number, then you feed that number into the same program and keep doing it. So that's called iteration and integration. In practice, this might be much faster, much easier to do. But there is a conceptual thing that I will not emphasize so much in this course, but if you take this advanced nonlinear dynamics, it'll be very important. So that's the main lesson we have learned from 2-dimensional flows, which survives going to any dimension. Many, many other tricks are totally useless. You don't want to look at null lines and things that are specific to 2 dimensions, and you'll never be seen again, but this is not one of them. Let's look at the simplest example. It was something that looked crazy in X and Y coordinates, but it was just a cheat because it was a complicated way of writing one linear and one nonlinear, but uncoupled equations. So this is a cheat. It's in 2 dimensions, but they don't care about each other. So this is really 1-dimensional problem. So in that problem, the space was X and Y coordinates. It was a plane, arbitrarily large. Origin, which was important because when you go to radial coordinates, there is origin of radial coordinates. So this is the state space. It's 2-dimensional. That means the Poincaré section should be 1-dimensional. And indeed, what we can do, we can forget that we are moving in theta and just look at the system where theta is a 0 or multiple of 2 pi. So that's this line here. So I pick out one particular radial direction. And now if I take any trajectory starting in this Poincaré section, if it's close to the origin, this is radially unstable, so the thing will spiral out and it will intersect this line. So go from x0 to x1. It'll do that again, and it'll be approaching the radial fixed point at r equals 1. So there is a radial fixed point in this section. And if I started from the outside, I would go to that point. So the periodic orbit is a circle. There is origin, which is equilibrium point, but then there is a circle. And that's all that happens in this problem in terms of invariant quantities. And if you do Poincaré section, circle is reduced to a fixed point. And now the cheat was in this particular problem that everybody rotates the same velocity irrespective of how far you're from origin. So the flight time, it's 2 pi for everybody. That makes it very easy. You don't have to compute flight time. So this is section, Poincaré section, S, and it's 1-dimensional. What does this Poincaré section look like? Convenient ways to plot, as we did at the very beginning, of course, when we look at 1-dimensional systems, to plot the Poincaré map, the return map. And to do that, let's say, so flight time was boring, nothing there. It just t equals 2 pi for everybody. But, you look at this equation. This is dr over dt. So you can write dr and then multiply everybody by t and then divide by r1 minus r squared. And now you can, to find the Poincaré section, you just integrate this over 0 to 2 pi. On the right-hand side, you just have a constant. So, this is 2 pi. But on the left-hand side, you have to do a little work. And you find out, you can analytically find what PR is for any initial point on the real line, where you land. That's just this integral after 1 pi. And that looks like, it doesn't really matter because this is the only time you ever see this, because all the books that I know only do this example, because as far as I can tell, there are no other examples which are exactly integrable and whose stability is also exactly calculable. R equals 1. It's attractive because its slope is smaller than 1, so the neighborhood shrinks. If you look at neighboring trajectories. And now there's a little trick which is very convenient for visualizing such flows. It's called such maps. It's called cobweb. And what it says is if I start someplace, let's say this is my initial point, I evaluate the value, then that's supposed to be R1, my next point. But the way I compute R1 is I go to the horizontal where I cross the unity, and that height is initial value for the next iteration. Then I evaluate that function. I go back. I get R2. And in this case, I get a rather boring sequence, but I don't have to actually write this thing. I can just draw by hand how it works, tuk, tuk, tuk. And I can, compute it as well as I want to. So this is how I understand, in terms of not differential equations, not trajectories, but in terms of maps, Poincaré maps, that I have a fixed point, which is a Poincaré section of a periodic orbit. So this fixed point means I have an orbit of period 1, because I iterate this only once. And that orbit is attractive, and everything can be computed very nicely about it. The thing that was very important so far was not just finding whether you have invariant solutions like fixed point cycles, but also what their neighborhoods do. What's their local linear stability. For this, I have to be both careful and insistent, try to be very precise. When you study chaos turbulence, you cannot afford to be sloppy here. You really have to be clear-headed. So let me try to define things carefully. So there are two notions of stability, which you don't notice when you look at equilibrium, but you definitely notice when you look at trajectory. One is local, that, it's some instant in time, small step in differential equation, my neighbors are, moving closer to me or away from me infinitesimal in various directions. So that's a local thing, and that is per unit time. So that's called rate. And what it does is I have a neighborhood, I start out with 100 marathon runners or something. That neighborhood gets sheared. Some get ahead, some get further out, closer in. So it's being sheared. And this local stability is very hard to visualize, at least for me. It says at every instant how the shearing is happening. So dynamical systems in terms of continuous time is often defined as first order of a position or state of the system. So X doesn't have to be coordinate like X, Y, Z, but it could be, temperature, pressure, or some other set of things. Let me call this V for velocity. So it's changing in time with velocity, moving. Strogatz uses letter F because it's a function, so he calls it a function. A little more carefully, X is a function of where I am. That says that I'm looking at autonomous systems where the local velocity of my state doesn't change in time. And you're doing that all the time when you're plotting this very beautiful MATLAB and mathematical plots, which says that if I look at some point, it's moving this way. That's this velocity vector, this way, that way. In plane, they look like this. And, in higher dimensions, they're very, very hard to visualize. That's what the first equation says. This velocity field is given. That's a law, and it doesn't change in time. So system is called autonomous. And this picture works in d dimensions, not just in a plane. If I want to find infinitesimal deviation away from my trajectory, I look at xi. So look at xi and a neighbor. And image I have is, this neighbor, there is actually a cloud of close by points. I'm starting with 100 or 1,000 other runners at the same time. And, this is distance to one of them, but could be any of them. This distance will be changing. My position will be changing in time, but also the distances will be changing in time. So this thing depends on time. So now if I take a derivative of a neighbor point that's some distance away, I get derivative, sum of the derivatives. I just take derivative of both. But this is one particular neighbor, delta x away. So I have precise formula for his or her velocity, because somebody who is, higher or lower me on a hilly landscape has a different velocity. Now this is infinitesimal, so I can take a derivative, Taylor expansion first term, and then I can look at how this guy changes with respect to all the components of dxj. And then I have to sum over all of them. And this is how a neighborhood will change in time. It's controlled at every instant by this matrix. The first two terms cancel because they satisfy the equation, so I only have equation for the deviations. And the equation for deviation says d dt delta x, that's this term, equals what's here. And this matrix has a name. I call it stability matrix. It's a d by d matrix. And I can take care of what happens to deviations by writing something called equations of variations, where I take my original equation and I integrate it. This is a velocity at every instant, and as a result, I get a trajectory. But now I can look at its neighbors, any neighbor, and that neighbor is evolving on this trajectory by a varying matrix, because this depends, velocity is different point, and this derivative is different. So this stability matrix or velocity gradients, its dimension is, if I look at just dimensional analysis of it, it has dimension 1 over time, because this is length over time, this is length, so this is 1 over time. This is something that changes in time. So that's a rate of shear. And by shear, I mean the neighborhood is being deformed instantaneously. So this is one matrix. Now there is another matrix that is what we really care about when we have motion in dynamical systems, because what we really care about are the solutions for dynamical systems. So we obtain where we are at time t by starting at time 0, ith component in the dimensions, and then we integrate the velocity at that position that is changing. So velocity is changing from 0 to t. That's how I get where I get there. And let me just call this whole thing function t of initial point. So this thing is a map. Solution of differential equation is a map. What does it do? It takes a point in the space and maps it into another point within the space. So that's what we call a map. And it depends where you started and how far I go. Now, if I look at the neighbor of that map, so I look at a point close to the initial point, do the Taylor expansion as before. Now I have to take derivatives of the map, not of the velocity, but the map. And that thing is a Jacobian matrix. What's a Jacobian matrix? Jacobian matrix is description of how you linearly change neighborhoods by finding the variation of your final state as a function of your initial state. So this you did at time 0, but this is 2 hours and 7 minutes later if you're very good in running marathons. And this object is dimensionless. And it was invented by Jacobi, German mathematician who was studying changes of coordinates. So this is a D by D matrix. It compares length to length, so it's dimensionless. And what it says is that if I had at initial time some slight deviation, sufficiently slight so I can think of linear neighborhood at initial position, and I moved on trajectory time t, I'll get my deviation at finite time t later. So this is final time. It's totally crucial, and it's kind of embarrassing. You must not mistake a logarithm for a number, logarithm number, and you cannot call logarithm Jacobian and the number Jacobian. It is not nice. It's historically wrong, and I don't know, my colleagues do this, but they do it, I guess.
So I did have one question as well. If you are in a neighborhood of a point, the Jacobian tells you how that neighborhood changes in time.
Finite time afterward. That's important from Poincaré sections because you go a long way and then you come back. What happens in Poincaré section is you only see finite time. Infinitesimal time, I can't even draw a picture. It's very confusing to think of shear because this is a tensor quantity. It says that every vector, every place in neighborhood is change in the J component. I don't even have a picture of it. But Jacobian is a totally logical thing. You take a square, you get a rectangle by linear transformation. And it's a matrix, it has eigenvalues, eigenvectors, it has natural coordinates. So everything is well described. If you find eigenvalues and eigenvectors of a velocity gradient matrix, that changes every second as you go around. So, I don't know what it does. But the other thing, I know what it does. It's transported by the flow and it comes back. So, for example, if you have eigenvector on periodic orbit, it does something, but it comes back exactly where it started, the eigenvector as well. And it just gets rescaled by the multiplier. So you understand what stable, unstable directions are. But if you do this for matrix of velocity gradient, it only works for equilibria, because for equilibria, there's no change. So, you find it once, it's all the same. But for anything else, it doesn't work. In the other course, in Keo's book, I spent like 3 or 4 chapters banging this into the innocent minds, because I can't bear it. People confuse logarithms for numbers. It's too painful. And it's due to bad teaching. It's not their fault.